now we finished our fun little distraction. So, Qs. So we finished talking about the Qs last time, and we were doing like, okay, when we DQ, when we NQ, we add it in, when we DQ, we take from the front. Then we talked about funny edge cases about, well, what if the node, what if it's empty, right? What does front and rear point to? No. What if there's only one thing in it? Well, they're both going to point to the same thing. So we have to keep those edge cases in mind, but the general case is like add to the rear, add to the front. Or remove from the front, pardon me. Is that what you're going to correct me? Thank you. So, let's start with the top of our header. What do we have? Well, we want it to be generic, and we're making a linked structure, so we're going to want to use those generic nodes. So, we're going to need a couple attributes. Who remembers the attributes we wanted? Front, rear,
Count.
and count. What's the type of front going to be?
Node. Generic.
Generic node pointer. Yeah. And rear, generic node pointer. And what size? Well, it's an int. I notice a lot of people in lab, when they get a little find and replace heavy, when they're changing the types from like int pointers or something, they're just replacing all the ints to type T when going generic. But of course, size still needs to be an integer, right? Some people, they left it, it was funny. Some people changed it to T. And I'm like, oh, this is wrong. But, like, but it worked. I'm like, only because you got lucky and made the type of type T int. You just got really lucky. As soon as you make it as a string, if I ask like the size of this thing is hello, you're gonna. That doesn't make any sense, right? Of course, it's got to be a number. So be careful. All right. Our constructors, we got our default, our copy constructor, our deconstructor, good stuff. And DQ, InQ, get the first, get the size, is it empty? Any questions? No. All we're doing is setting it up. This is just saying, remember, it's kind of like saying, this is what you can do. So far, does this tell us how we do any of the stuff we can do? No. All we know is, oh, we can add something. And when we want to add something, we give it an element. When we DQ something, oh, it returns something. But it doesn't say how it's happening. That's what we're going to start writing now. So let's start with our default constructor. When we start with a Q, what should its size be?
0.
That seems reasonable. What should the front and rear point to? Probably nothing, right? Yeah. Seems reasonable. Any questions about this? Okay. So we're going to skip the copy constructor and deconstructor for a moment. We're going to come back. So let's jump to InQ. You can probably tell from the amount of space that it might not be that simple, but hang in there with me. It's really not that bad. Let's just break this down. It gets complicated because we need to start worrying about those funny edge cases, right? Is it empty? Does it have one thing? We got to think about these things when InQing. So here's what we're going to do. And understand that the way I've coded this, how many ways are there that I could code this? A lot, right? So I'm just showing you one. You could code it a little bit differently. I like the way I coded it, but if you don't like it and you want to write it another way, cool, whatever. If it works, I'm happy. So let's have a look. If it works and you didn't make other funny mistakes, I'm happy. So here's what we're going to do. If we're adding something, we need to create a new node that's going to hold on to the data we want to add to the queue. Because remember, those nodes are kind of like analogous to the information in the array when we were thinking of the arrays before. So the node is going to hold on to the information. But the stack itself is just a series of nodes, and the nodes has the data. So we need to make a node and put the data inside of it. What data? Well, the data we're trying to enqueue, so element. So where do we put this? Well, if is empty. So this is just calling the function. I could have easily put this is empty, but I didn't because I'm lazy. So if it's empty, what do I have to do? Someone's got to tell me.
That will be the first element.
Exactly, it's the first thing. So if it's empty, we'll do this. Rear, front is no. Okay? Otherwise, we will say rear set next to node. So let's take a step back and think about what's happened so far. We'll get rid of our salesperson and our accurate map of Nova Scotia. Okay. So let's do the general case. So let's not think about it's empty right now. Let's assume it's not empty. So we have front, I'm just going to draw that as an F pointing to some node. And this is rear. Okay? So I want to add something. So I create the new node. Here's the new one. And I put elements in it, whatever. And it's not empty. So if it's not empty, rear is set next to node. Okay, that's easy. So hey rear, your next is that now. Right? But then what am I forgetting?
Change the rear.
What?
Change the rear to rear points to one.
That?
Ah, yeah.
Exactly. I need to make rear not point here anymore. It needs to point to the new rear. Oh, and of course we have to increase count. So, who here, when I showed you what we do when it's empty, was like, well, wait a minute, you forgot to set,
Exception?
well, not the exception, that's when we're removing.
Oh.
Who here was thinking, how come when, like before you said, when it's empty and you want to add something, you need to set the front and the rear to, like the same thing? So let's take, just give me 1 sec. Let's think what would happen if it was empty. And remember, there's no magic going on. We're just following the instructions line by line. We're making no assumptions. When in doubt, don't think too much, just do what it says. So we've got front, which is like pointing to nothing, and we've got rear, which is pointing to nothing. So let's follow the code. Oh, create a new node, okay, cool. We put element in it, E. And if it is empty, front points to node, like front goes to node. Okay, good. So far, so good. We skip the else, and then we say, okay, rear's going to node. Oh, okay, yeah. Oh, checks out. Regardless of if it was empty or not, we want to set rear to node. Rear is going to be the new thing, no matter what. And of course, then we also update count. Isn't that clever?
Yeah.
What was your question?
Does the node have to point to a null pointer? Does it point to anything?
The new node?
Yeah, like the rear. Does that point to null pointer?
That's going to like point to null pointer, yeah. I mean, it depends on how we program it. It's possible that we don't have to do it that way, but you should not do it that way. Makes sense? Other questions? All right, cool. So let's DQ. Well, here, a good chunk of this is just going to be throw in an exception. If it's empty, that's a problem for you to solve, not for me. Right? The programmer who told me to DQ, but I had nothing in it, your problem, not mine. I'm throwing that exception. Otherwise, we're going to create a pointer so it's not empty. Something must exist. I'm going to create a pointer. This is just a temporary pointer, and it's going to point to the front, right? But remember, it's not pointing to the data. It's pointing to the node that holds on to the data. That's a very important distinction. A lot of people at this stage have a hard time separating the data from the fact that there's a node. The queue, when it's a linked queue, is a series of nodes, and there's data inside of it. Abstractly, the queue really, as far as the user of the queue cares about, it's a queue of data. But we know as the programmers of the linked queue that there's nodes there. So we've got to make sure we're deleting that node. So I've got this temporary pointer to hold on to the front. So let's say it's something like this. TD for to delete. we get the data that we actually want to return, and we're going to hold on to it. Front is now going to be set to front.getNext. In this scenario, what would front point to after this line of code?
Next gen.
The next one, but what's the next one in our
Null
scenario?
pointer.
Null pointer. Huh. I'm glad we're doing this first, because this is like the edge case. It's going to be null pointer, decrease count, and then if it so happens that it's empty now, we have to make sure we set rear to null pointer. Because otherwise, let's think about what would happen. Okay. I'm going to jump away from the edge case for a second. We're going to go to the general case to make sure that makes sense. Then we'll come back to this funny edge case. So let's say we're in this scenario. What do we do? Okay, it's not empty, to delete, great. Get the result, front points to the next thing. Okay, good. Is it empty? No, it's not empty, we're fine. Let's just finish off the code here. Delete, to delete, and return the result. So this gets deleted. Right? Then we return the result. Great, we're done. So now let's think about what happens when we have this funny edge case, where there's only one thing in there. So it's not empty, we set to delete to this. So far so good? Yeah, any questions? We're good? Okay, set it, okay, front, get next. So front now points to null. Okay? Decrease count. And now we would say, okay, is it empty? And it would be true because the count went from 1 down to 0. So is it empty? Yes. But imagine if we didn't set rear to be null pointer. I will delete, like to delete, we'll delete this. Right? But rear still thinks it's got a pointer to like a node. So we got a problem here. So we're going to be safe and say, rear, you also have to point to null, that special thing that means you're pointing to nothing. We just have to be careful about that edge case. Any questions about that?
Once we delete the object itself, that rear will be pointing to null.
It won't be pointing to null, it'll be pointing to a chunk of RAM that it was pointing to begin with. But that thing is now not there. But it's not null. Because null and not the thing you're looking for are separate. Null is like that special value that means it's pointing to nothing. Good question though, yeah.
In that case, should like something deconstructing that like go through them and make them all point to?
Oh, that doesn't matter because we're getting rid of them anyways.
Yeah.
Yeah, don't care. Good question though. Okay. We get the first. Oh, yeah.
Hypothetically, if you forgot to do that rear equals null pointer, what happens? Does it just crash or does it just create a memory place?
Well, it depends on how we programmed it. Like if isEmpty was, oh, is front and rear both equal to null pointer? In that case, I don't think it would crash, but if it was doing like some sort of count thing, or maybe, no, it would mess up, right? Because if, oh, is front and rear pointing to null? Well, it would be no. But even though it's actually empty, because it's not pointing to null. And then what happens if we try to add something? And rear thinks it's pointing to something, right? Rear thinks it's pointing to a node, but that's not there. And rear's like, oh yeah, you know, hey, what's your data? Oh, null pointer, it's the whole thing. Gotcha. So first, well, if it's empty, do nothing. Otherwise, return the data from the front. But we don't have to do any of that extra fancy stuff because we don't want to remove it. That node's staying there. We just want to get what the data is there. That's all. Size, return count is empty if count 0. Okay, great. Copy constructor, well, this is going to be very similar to the stacks copy constructor. Go through and make a copy the whole way down. But we got to make sure how deep is that copy. We have to keep that in mind. Deconstructor, well, it's not empty, keep dequeuing. Dequeuing is actually going to do deleting for us. So we'll just have the deconstructor call dequeue and just dequeue everything. And delete it all. Dequeue does the delete for us, it's handy. I could have coded this to basically be the same thing as dequeue in a while loop. But I'm lazy and this is just good use of being a good computer scientist. Be lazy. So, what does the CPP file look like? This is generic. What would that look like? It's like nothing, yeah. So we can do some quick tests. I'm not going to go through this. This code is online. You can play around with it if you want. So here's a question, or here's a point. I just defined a regular old queue, but we can have other types of queues where it's like a first come, first served basis, but of course, maybe there's a bit of a twist to it, like a priority queue. Priority queue, we might want to maximize or minimize priority. And you're going to need priority queue in assignment 3 if you're doing A star. And you're going to build a queue with however you want. Well, whatever it says in the assignment, because I don't remember what I wrote. Who here has ever been to the hospital? You ever go to the ER? Yeah. When you go to the ER, is it first come, first serve? No. Right? If you've ever been to the ER, you know that, right? So, what is it? What do they do?
Wait.
Prioritize.
You wait. But why are you waiting? It's because they like triaged you, right? They assign like a priority to you. Like if 2 people come in with the same priority and you showed up first, you get to go first. But really, they're prioritizing people who need help more than you. So there's a priority queue. So it's like a queue. Everybody who shows up will enter the queue. But whenever we dequeue somebody from a priority queue, we're not necessarily dequeuing the person who's at the front, like who was there the longest, like the first one in. We're dequeuing the one who's got the next lowest, highest, depending if we're maximizing or minimizing priority. Now, let's take a second and talk about this. Hopefully it's only 1 second. We've got 2 ways we can do this. All that matters is that when I dequeue something, I get the individual, the thing with the next priority. That's it. But I have 2 options. Here's what I could do. I could in-queue everybody such that every person who shows up, I figure out their priority, but every person that shows up just gets appended to the end of the queue. So that's the in-queue. What's the computational complexity of doing that? Just adding something to the end. Constant. It's constant because we have a pointer to the rear. If that's the case though, when I dequeue, I need to find the person, the individual, the thing with the next priority. How long is that going to take? And because I have to do a linear search. Right? So if we implement it that way, in queue is order 1, dequeue is order n. But I could do it the other way, where when I dequeue, it's going to be set up such that the next thing, like the thing at the front, is the one that I want next. The next priority, whether it's high or low, whatever. But that would mean, so that's order 1, just take away from the front. But that would mean that my in queues, I need to do a linear search and find where to put it. So how long would that take? N. So what's better? Well, you win some, you lose some. You do it that way, oh, you win here, but you lose there, or vice versa. It's interesting. Because all that it doesn't matter how it's implemented. It matters that it works the way it's supposed to. That when I dequeue, I get the thing with the next priority. All right, we'll pick up here next time.